Hi, I'm David Dianasopoulos. I'm an electrical engineer here at Supfina Machine Company. I graduated URI College of Engineering in 2011.
Hello, my name is Mason Dumaine. I'm also an electrical engineer here at Supfina, and I graduated from URI class of 2019.
Supfina Machine Company is a small group part of a larger group called the Grieshopper Group. We were established in 1984, and we have a small workforce ranging from 40 to 50 employees. Here in our North Kingston branch, we research and develop our super finishing and flat finishing product lines. We service our customers in the North America region, which includes the United States, Canada, and Mexico. Our sister company, Supfina Grieshopper, does similar jobs as us, but services the European and Asian markets. Our two product lines that we focus on in the North Kingston branch is super finishing and abrasive finishing. Our super finishing markets deals with the automotive and bearing industry, where the abrasive finishing deals with flat finishing, double disc grinding, and fine grinding. So what is super finishing? Super finishing is a machine process that improves part geometry. It only removes a small amount of material. To achieve this, we have different methods using an abrasive finish. They can either be tape finishing, stone finishing, or a cup wheel stone that rotates around an axis. Depending on what the part geometry is or the amount of materials, the appropriate method will be used. Since we only remove a small amount of material, we refer to this material as microns, such as how many microns is removed. To give you an idea what a micron is, take a look at a paperclip. A paperclip is fairly small with a wire gauge of 1 millimeter. So it would take 1,000 microns to equal that same size of the paperclip. As I mentioned before, our job is to improve the geometry. So we look at the incoming from our grinder and we can see the different profiles of what the workpiece looks like. After a super finishing, we verify these profiles and we can hopefully achieve the tolerances that is specified in the prints. When we look at the surface of the workpiece, there are two statistics we look into. The first one is roughness average, which is a cumulative average of the height variations from the center point. The other statistics we look at is RZ, which is a roughness depth. That is the distance between the highest peak and the lowest valley. Our goal is to decrease or make that number or that statistic as small as possible. The smaller the value, the better the surface of the workpiece. As a manufacturer and a machine tool company, we do pride ourselves to doing the best work as possible. But problems do arise, so we have to ask ourselves these questions. What happens if we don't achieve proper finishing results? Why is the machine behaving differently all of a sudden? How will we know what the root cause is? Is there a way to prevent this from happening? And how can we assure our customer will be satisfied?
Well, that's where you come in. Supfina is looking to answer those questions and more through a comprehensive industrial IoT platform. By aggregating machine health, process, and part data, Supfina will create a central hub, feature-rich with service and analysis functions. Supfina's IoT platform will be machine agnostic, capable of interfacing with any machine or control scheme, and the functionality will be presented to end users in an accessible UI available on common devices. The system won't just bring connectivity to singular machines. It will facilitate network connectivity across an entire manufacturing line and unify communications regardless of control platform. It will also have flexibility for both simple edge computing and cloud operation applications. Previously, machine communication has been limited at best. Connection to a network is rare and usually reserved for remote debugging of machines. Intra-machine networks are common for machine control systems, but are rarely extended. The connection and monitoring of an entire line is pretty novel. One of the difficulties in monitoring an entire manufacturing line lies in the huge variety of control platforms and configurations. Each machine could have a different control system with different requirements. Fortunately, there are several communication protocols that simplifies this and translates data into a common format. These communication protocols are used to collect data from any computer at any location. This collected data will then be stored, analyzed, and displayed to the end user through Supfina's IoT platform. This is a short video giving an example of the kind of machines and processes that Supfina works with. Just in this relatively simple machine, there is a large amount of data to be collected about the process. Machine health statistics can be gathered by monitoring motor vibration, temperature, and load. This data can then be used for predictive maintenance, reducing machine downtime. The process can be further optimized by comparing data points like motor speeds to post-process measurements of critical features. All of these functions and more will be important features in our IoT platform. The objectives for our capstone designers are as follows. The electrical engineers will identify the data to be collected, specify sensors and hardware, create electrical schematics, generate a bill of materials within the project budget, and integrate and test the hardware. Our computer engineers will design the structure of the web server, develop methods to test and display machine data to the web server with a focus on modularity of design for future expansion and functionality. So, to summarize, Supfina would like to build an IoT system that records and collects process and machine data using hardware designed for standardization, to create a system that can be integrated to Supfina and non-Supfina machines, and build a user interface that Supfina and its customers can access anywhere in the world. Supfina would like to thank you for your interest in our 2020 ELE Comp Capstone Design Project.